Welcome back to ECE 442-542. Announcements. Homework 6 is due tonight. Based on office hour traffic, I'm guessing most people know that. There is material on D2L to help you with homework number 6. Hopefully you found that before now, if you're just now watching this. And there is a special root locus, two poles to the right of a 0. Those are two real poles in general, where we can now use the geometric mean to determine that. Those two additional pieces of notes and video are on D2L. Exam number 3 review session is immediately following class at 7 tonight. And there is an additional lecture. This is really lecture 6.3 today, right now. There's a lecture 6.4 that talks a little bit more about PI control design. That should already be available to you on D2L. Hopefully, knowing or seeing that the exam is the next time we meet in this room isn't coming as a surprise. Exam 3 is Wednesday. Today what I want to do is talk about the process for exam number 3, and that you can see on the screen. I've decided to type this up instead of handwrite it. I can get more on the page that way. Then we will go over proportional and PI controller design. And we'll do that by reviewing a proportional controller. Then we will introduce what we mean by a PI controller, and we'll derive that. And after the derivation, essentially you'll be able to just take the structure and run with it. You won't have to rederive it when you're applying a PI controller. And essentially we will see that we end up with 2 adjustable parameters, the gain and the 0 location, when we have a PI controller. Then we will summarize the 3 root locus rules. All of this will be on exam number 3, and we'll try to illustrate that with an example showing how we could progress from a proportional design to a PI controller design and why we might want to do that. The process for exam number 3 should be consistent with what we had. There is one slight twist. I want you to bring a photo ID and have that on your desk. Something happened in the last exam. That's as much as I want to share. And it would be helpful to have a photo ID and probably a cat card, something with English writing on it that I'm sure you have other photo IDs that might not be in English. I wouldn't be able to read that. But I want to compare your name with your photo. And then we'll have 3 sheets of notes, front and back, and those sheets are obviously limited to the normal size, 8.5 by 11 inches. You can bring any calculator. Obviously the Inspire, the HP 50, whatever it is now, 51. Not, oh, but this is a calculator, and you bring in a laptop computer. That's not what I constitute as a calculator. Or your cell phone or smartphone, that's not a calculator. So a standalone calculator. Transform tables, you could bring both, I guess, if you want, from exam 1 and 2. And something to write with and sketch with, measure with, etc. And then there's all the subsequent no's. No cell phone, no computer, no textbook, no class notes, and no neighbor. I'm going to quickly go through where we've already been. Proportional control, you should just be seeing this diagram. When you hear proportional control, now you have a gain, K, in this closed loop configuration with a plant, G. You can derive the transfer function, or you can simply remember it's CG over 1 plus CG and plug in the appropriate C's and G's. And then if you're interested in the dynamic behavior of that closed loop transfer function, that's governed by the denominator in that t sub c of z expression, which is 1 plus k g of z when we have a controller c of z being proportional. And that's really going to give rise then to this characteristic equation, 1 plus k g of z equal to 0. We're interested in the values of z that make that happen or satisfy that equation. And that can be satisfied for all these k values from 0 up to infinity. If you wanted to iteratively determine different closed loop poles for different values of k, you could plug in different values of k and find the roots or the values of z that cause that to be true. PI control. Now we've added an I to the P. We now have a PI control, and in the analog sense, we now have a proportional term. It's proportional to the air signal E. The air signal is the same. It's just in the P term, we're scaling that air instantaneously with K sub P. In the I term, we're integrating that air, and now this is collecting information that's happened in the past, and we're using that to help us control the system. If we take that into the S domain, we're now simply realizing that the integration operation is 1 over S in the Laplace setting, and now we have K sub PE plus Ki over S times E. E is common to both pieces. We can factor that out, and what we want to do is actually find this PI controller in a discrete setting. What's the transfer function associated with a PI controller? What's the transfer function of a P controller? That's just K. That's an easy transfer function. What we want to do now is try to find the transfer function associated with a PI controller. And there's all sorts of ways of finding discrete equivalence. We know that. Let's just use one that actually gives us a fairly straightforward discrete equivalent. Maybe that title is misleading, saying discrete equivalent. People think all of these are equivalent. No, it's just a discrete form of the analog version that we had before. Now we're going to use the forward rule and replace S everywhere, and it only appears once with this expression z minus 1 over t. We now have K sub P times E, and we've simply changed the arguments on U and the air, and scaling the second term is now what's associated with the integrator piece of our PI controller. We can get that t that's in the denominator of the denominator upstairs, and collecting the common terms that scale E, we're starting to get close to a transfer function between the air signal E and the input U to the plant. For a discrete time or a discrete version of this PI controller. We'll get even closer if we put both of those terms over a common denominator, which is z minus 1. Hopefully these steps don't confuse you, but they may go by pretty fast the way I'm scrolling through them. But now we see that we have a numerator polynomial in z, and we have a denominator polynomial in z, and what is fixed in that representation and what can we influence? We can influence K sub P and we can influence K sub I. And we're assuming that t has been given to us, the sample period. Once that's given, then the only thing that we can adjust are these weights on the proportional term and the integral term, and those are the K sub P and the K sub I coefficients. Now I've scrolled up a few lines, but I'm simply combining that numerator, the terms in the numerator, and then factoring out the scaling term on the z so that I can now see explicitly the zero factor. The zero factor now is some ratio of these adjustable terms, and the gain that weights that zero factor is the proportionality gain, k sub p. If somebody gives you k sub p and k sub I, those two parameters are determined. We know k sub p and we know this alpha. Alpha is the zero location. And that's really what I want you to focus on now. For a PI controller, if I say design a PI controller, you don't have to go through this derivation again. You can just say, oh, he wants a PI controller. I'm going to give him this generic structure. I actually have a fixed pole at the origin, and that's consistent with what we had before. In the analog setting, we had a 1 over s. We had a pole at the origin. And the origin in the s-plane corresponds to z equal 1 in the z-plane. So that now we have a pole at z equal to 1 in this PI controller. We don't change that, but we can play with where the 0 is located and the gain k sub p on that controller's transfer function. We now have a first order transfer function between the air signal E and the input to the plant U, and we have these adjustable parameters. I'm not probably going to ask you find k sub p and k sub I. You could do that given enough time. You could back out those values, and then if you had a PI or a PID controller in a box, you could now turn the k sub p dial, you could turn the k sub I dial once you found those. But in this class, it's enough to say, oh, I'm going to figure out where I want my 0 to be. That will determine alpha. And now I'm going to use what we've been using, a root locus strategy, to figure out what I want that gain k sub p to equal. And I'm stuck with a pole at z equal to 1. PI controller, this is what you see. K sub p times z minus alpha factor divided by z minus 1. What are some of the properties? And I received some of these as questions for the exam review, and I'm going to kind of cover some of those now because it's appropriate. We ended up automatically with a pole in this PI controller at z equal to 1. That pole at z equal to 1 actually improves steady state accuracy. And what does it do? It actually forces, if we can stabilize the closed loop system by the choice of our 0 and pole, if we can stabilize the closed loop system, then if somebody injects a constant reference signal into that system, you will track that reference signal after the transients have disappeared with 0 air. You'll have no air between what you inject, if it's a constant, and what you see at the output of your system, because of that open loop pole being at z equal to 1. And you can see that if you go through the final value theorem and try to figure out, oh, what's the final value of the output y in the time domain given a constant reference input r. But that's one property of the PI control. It improves steady state accuracy. And remember, what we're doing in a control scenario, we're typically trading off steady state accuracy for transient performance. The fact that we now throw in a PI controller, we may be sacrificing some transient behavior, but we're trying to now trade that off with, oh, now I have better steady state accuracy. that may be the result of obtaining this steady state accuracy. We just stated earlier that if you now have a PI controller, you have an adjustable zero location, that was the alpha, and you have an adjustable gain. And if we wanted to compare those, now the PI controller, we bought a Vanna, so we have an I, cost us a little. What did it cost us? Maybe some transient behavior, but now we have two adjustable parameters versus one with just the P controller. Let's now look at the block diagrams that I want you to be thinking about when somebody says a PI controller. We started today saying, oh, if we have a proportional controller, what was in that C of Z block? Just a K. Now I said we have a PI controller. Now we say, oh, we just derived the PI structure. That's K times Z minus alpha over Z minus 1 for whatever plant, G of Z. That's now the block diagram, closed loop, of a system that's controlled with a PI controller. We can now convert that into our standard root locus structure by sliding that zero factor and the pole factor into with whatever that just meant, but into the block with the plant, so that we've now created a G bar. We haven't changed anything in the system other than now we've isolated this parameter K bar, and we've put two new factors in to modify the plant, and now we're going to call that modified plant G bar. The only thing that we haven't really committed to is that value of alpha. We can now pick an alpha, and then we have a fixed G bar. Oh, now we're in the traditional root locus controller design. I now simply plot poles and zeros of G bar, figure out what K bar or what the root locus looks like, and then pick a K bar that gives me the behavior or the performance that I'm after or that I'm looking for. We haven't had to use any new formulas. The closed loop transfer function is still CG over 1 plus CG. And if we push those two factors, a zero factor and a pole factor, in with G, we can call that now a G bar. And we have K bar, G bar over 1 plus K bar, G bar. Structurally, this looks just like what we had with the proportional control. The slight change is that now in G bar we've had to throw down a zero factor. We've had to now put onto the Z plane a Z minus alpha factor. And we've also thrown a pole factor in there. But it was fixed. It's fixed at Z equal to 1. And if you remember back, if you were taking the earlier class, we had two shakers, didn't we? We had a pole shaker and a zero shaker. We can still have that here. We now have our pole shaker, but it throws out a fixed pole at Z equal to 1, and the zero shaker, now we have some variability there. So you have your shakers on the table for the exam. You can season your plant to hopefully produce the closed loop behavior that you're after. Again, we have this characteristic equation that we're playing with. Now we're looking at 1 plus K bar G bar of Z equal to 0. That's the same structure that we've had all along when we've talked about a root locus. If we look at the numerator, or if we obtain a common denominator of 1 plus k bar g bar, where g bar now I'm saying has a numerator polynomial n over a denominator polynomial d, that's the notation that I'm using, then we can rewrite 1 plus k bar g bar as simply d plus kn over d. And when we set that equal to 0, we're really looking at when is the numerator equal to 0, as k bar varies from 0 to infinity. And when k bar is 0, that second term vanishes, and we're just looking at, oh, those were our original open loop poles, the values of d of z that cause d of z to equal 0. Then if we let k bar get really, really big, then some of our zeros are going to be the roots of n of z. And if you hear me talk about the numerator of t sub c of z's denominator, hopefully that won't confuse you, but that's what I'm really saying. I'm looking for d of z plus k bar n of z. That's the numerator of the denominator of t sub c of z. I'll just make you speed read for a little bit longer. And what you're reading now are the rules, and I'm assuming that you've already written these down a time or two, and if you want them, these are maybe stated slightly a little different way, but you can go back and pull this PDF up off of D2L. Today what I really want you to do is focus on what's being stated in these rules. Rule 1 is, where do we start and where do we end on a root locus diagram? First, how many branches do we have in our root locus diagram? How many branches do we have? So the number of poles and zeros plus 1. Is that the number of branches we have of our root locus? How many branches of the root locus do we have? Any other thoughts? Yes? Pole zero excess. So we have some different answers going on, and they are kind of connected to the answer, but not quite. Number of branches that we have of a root locus equal the number of roots that we start with in d of z. So how many open loop poles did we have? And that open loop poles could include poles that are in our controller, meaning it might include this z minus 1 factor coming in from our PI controller. So it's the poles of g bar of z. How many of those do we have? Boom, that's how many branches we have. Now, how many branches go off to infinity? That's equal to the pole zero excess. Let's say that we had a pole zero excess of 2, and maybe we had 4 poles in g bar of z. Now we have 4 branches of our root locus. 2 of those branches will terminate on finite zeros, these zeros or these open circles in our complex C-plane, and 2 branches will go off to infinity. Those 2 branches going off to infinity are the pole zero excess. That's maybe more than what we bargained for on Rule 1. I just wanted to know, where are we starting and where are we stopping? But this kind of tries to tell us. We have branches equal to the roots of d of z equal to 0. So you look at d of z as a polynomial and you say, how big is that? What's its order? If it's 5, then you have 5 root locus branches. Why is that important? Because maybe you just have 3 real axis segments associated with your root locus. Well, that means there's a couple of branches on some of those segments. I should just read and quit paraphrase or introducing more words than there are on the page. Just move on, is what I can see in your eyes. Okay, so here we're starting at the roots of d of z. That's where we start. That's when k is equal to 0. And then we end on the finite open loop zeros. Those are the roots of n of z, while some branches go off to infinity. And where do they go? We haven't really covered, other than the case when we have a pole zero excess of 1. Then where does that branch go? Where does our branch at infinity, where is it headed when we have a pole zero excess of 1? It's going down the negative real axis, isn't it? That's where we're going off to infinity. As we crank up the gain k, one of those closed loop poles is going to zip off to minus infinity. That's unstable. So we probably can't crank up the gain at will. We've also talked about a pole zero excess of 2. When we just had 2 real poles, then we have our branches going off to infinity are now at plus 90 and minus 90 in the complex z-plane. Rule number 2. Here's where sometimes you get maybe confused with, wait a minute, I have 5 branches and I only have 2 real axis segments, or 3 real axis segments. Then you may have some branches sharing the same real axis segment. Real axis segments in the z-plane, this is our French bread issue. We chop up our French bread. Where do we chop it? Where do we cut it? I shouldn't say chop. I should say, where do we slice that French bread? All of our poles and zeros that live on the real line, that's where we will have a slice. And now we just need to determine which of those pieces of our bread belong to the root locus. And that's based on the phase angle condition, but it basically, if you now go stand on one of those cuts and look to the positive real axis off to infinity, you now count how many poles and zeros are to the right, or do you see as you look to plus infinity on the real line. If you see an odd number, then where you're standing is belonging to the root locus. If you see an even number, then that particular line segment on the real line does not belong to the root locus. Rule number 3, breakaway and reentry points. Breakaway points and reentry points, we've really only talked about the case where we kind of have, either 2 real poles or 2 real poles and a 0. And we could have 2 real poles and a 0, and if that 0 is not lying to the left of those 2 real poles, then we may not have a breakaway. Sometimes rule 3 may not even exist. If you had 1 pole, do we have a breakaway or reentry? If we just had a system that had 1 pole, do we have a breakaway or do we have a reentry? No. We're just zipping off to minus infinity. No breakaway or reentry. We might have reentry and no breakaway. We might have breakaway and no reentry. We'll talk about that, I hope, in a few minutes. That's the plan. That's why I'm scrolling. now so we can get to more fun things. But this is kind of fun. You could almost think of this as something that's being set up on the mall. Are they setting up for spring fling? Now we have 2 poles and a 0. That's our spring fling. We're going to be flipping and moving around, right? Now we have a circular path. And that circular path is determined by this geometric mean length, this R, and hopefully it's clear how I've labeled it. The length between your 0, the center of the circle is determined by the location of the 0. And the radius of that circle is determined by these 2 lengths, their geometric mean. We can find what L1 is. We can find what L2 is. Those are numbers. We take the square root of their product, find the geometric mean. That's the radius, R. And that 0 could be positive, it could be negative. The poles could be positive or negative. You just need those lengths, the value of those lengths, the magnitude of L1 and the magnitude of L2. And I've tried to label the breakaway as this point Z sub B, that's a relative max, and Z sub R, that's the reentry point, is a relative min. And the gain value, K, that moves you on all of these red points is determined by this formula, and that's from the magnitude condition. You plug in any value Z on that red sketch, any of those branches. How many branches do I have? In this particular example, how many branches of the root locus do I have? In general, how many branches? I don't care if I'm on the real axis or on anywhere in the z-plane. How many root locus branches do I have? I just have 2, if that's consistent with what I just said earlier. I have 2 poles, don't I? I have a pole at P1 and a pole at P sub 2. I have 2 branches. They're going all over the place. One is going from, let's say, which one do you want to be? Let's let the little one be P1 and the big one be P2. P2 starts to the far right and it starts going towards the breakaway point as we crank up the gain K. Let's say at the breakaway point we calculate the gain K at that breakaway point, and let's say it's 2.76. Well, before we get to that breakaway point, the gain K is below that on either side of that point where they break away. That's why that's the relative maximum. If we had the gain at 2.7, one pole would be a little to the right of the breakaway and one closed loop pole would be a little to the left of that breakaway. And it's only when we get to 2.76 for K that we're right at the breakaway. We crank up the gain to 2.7. Now we've become complex closed loop poles. We've moved off the real axis. Now we crank up the gain, that knob, and we crank it up to 16.7. Now we're at the re-entry. It's bigger than what we had at the breakaway, but I said these are relative mins and relative max. Now, what did I just say? 16.7? I crank it up to 16.8. Now what do I have? Now I have 2 real unequal poles, closed loop poles. One is moving towards the 0, going to the right. The other one is going off to minus infinity. And what was my gain? 16.8. Where were those poles located at 16.7? Right at the re-entry. So we went from 16.7 as a gain to 16.8, 16.9, 17. Do you see that that was a relative minimum value of gain K at the but you could compute those for a given P1, P2, Z1, and gamma. But on an exam in the heat of the battle, you may not need to know that. You just say, oh, I just need to find the geometric mean. And once I do that, I can pull out my compass. And I can sketch this circle. And once I have the geometric mean, I know the radius, I can find the breakaway. Boom, I flip that around, and I now have the reentry. Is this system stable? Trick question. It's a trick question, isn't it? I haven't shown you where the unit circle is. Stability depends on where the unit circle is. So you would have to draw the unit, sorry if I scared you, but just a little bit. The unit circle is going to determine stability. If you, relative to all of that, well, we can do that later. But that is now two poles to the right, two real poles to the right of a zero. Gives rise to that root locus sketch. Let's look at an example. And we're really going to test our analytical abilities. Look at how involved that plant is. It's not very involved, is it? We have a pole at the origin. Is that plant open loop stable or unstable? If I just handed you G of Z and said, is this system stable or unstable, what would you tell me? If I injected a bounded signal into G of Z, would I get a bounded signal out? Yes. This has a pole at the origin, which is inside the unit circle. That's open loop stable. Now let's see what, so K equal to 0 stabilizes that. Obviously now somebody's getting all twisted. They're saying, well, when K is equal to 0, you have no transmission in the forward path. You have nothing. There's no, so don't get too worried about that. We're going to crank up the gain K and see what we have as K gets a little bit bigger than 0. Okay? So now as K gets bigger, we want to know, okay, it was stable. When K was equal to 0, then we really just had this system, is what I was saying, where this might be U and this is now Y. That was when K is equal to 0, and that's stable. Now, as K gets bigger, what's the range of K for closed loop stability? What's the closed loop transfer function? Have we changed anything in that structure of the block diagram? No. If you were looking for points, you would say, oh boy, I just hope he gives me some partial credit. It's what? Kg of z over 1 plus Kg of z. That's the closed loop transfer function. And what's the denominator of that? Well, the denominator does influence closed loop stability. The denominator now, we can look at 1 plus K, and what was G of Z? That was just 1 over Z, and we have that equal to 0. Or, this is now Z plus K over Z equaling 0. If we look at the numerator of the denominator, that's what's influencing stability. That's now what we're after. Or what are we trying to do now? K equal to 0 gives Z equal to 0 is the solution to that equation. we're trying to select values of k, non-negative values of k, select k greater than or equal to 0 to keep the roots of z plus k, well, the roots, let's just say the roots of this polynomial, z plus k, inside the unit circle. So we can only crank up k so much that when we solve that for z, we keep all of the z values having a magnitude less than 1, right? That would be inside the unit circle. Or if that was not very clear from that linear polynomial or first order polynomial, you could say, or you're now looking at 1 plus k g of z equaling 0, which now says that k g of z is minus 1, which is 1 at minus 180 degrees. Or we now have two conditions that need to be satisfied relative to the root locus and stability. We have one which says that the magnitude of k g of z is equal to 1. And the second condition is that the angle of g of z, here we're assuming k is greater than or equal to 0, so it doesn't change the angle relationship. This angle is 180 degrees. Suppose we look at the first one, the magnitude condition. If k is non-negative, we can factor that outside the magnitude. And we know what g of z was. And the magnitude of a ratio is the ratio of the magnitudes, and the magnitude of 1 is 1. This now says that we have k times 1 over the magnitude of z equaling 1, or that k is equal to z. And I think you already have sketched mentally the root locus of this example. If I wanted to sketch the root locus associated with this problem, what do I put on the z-plane first? Pardon? A pole at the origin. I don't even have any finite zeros, do I? I just have one pole and it's at the origin. I can now plot or sketch that. And what's the root locus look like? What's my French bread look like? It looks good, doesn't it? It's infinite in either direction, the right side or the left side. Which of those segments or both belong to the root locus? Now if I stand on the positive real line and look to my right, do I see an odd number of poles and zeros? No. What if I stand on the negative real line and look to my right? Then I do see an odd number of poles and zeros. I have one branch. I have a pole zero excess of 1. I'm going off to minus infinity as I crank up the gain k from 0 to infinity. And if I sketched the unit circle, there's 1 and -1. Does that help me with this question of stability? At k equals 0, I'm stuck at the origin. But now as I crank up the gain k, at some value of gain k, I'm going to exit this unit circle, and that would be a gain k that would drive my closed loop system unstable. And what I really want to do is figure out what will get me to that particular box. What gain value k. So I'm looking now for the maximum gain value for stability. And what was my expression for k? It was just the magnitude of z. I can now say, oh, this is the magnitude of z evaluated at that box, which is, the box is located on top of z equal to -1. Oh boy, this is getting very challenging, isn't it? The magnitude of -1. 1. So what's my range of k for stability? I have a stable system for k living between 0 and 1. Let's just pick a k. If I said pick a k that would stabilize the system, you now can pick any k you want between 0 and 1. Suppose k is equal to 1/2. Is the closed loop system stable for that k? Yeah, that's what we just derived. It's between 0 and 1/2, so we have a stable closed loop system. And what's our closed loop transfer function? That's kg over 1 plus kg, k over z over 1 plus k over z, k over z plus k over z plus k. And we said that we wanted k right now in this example to be 1/2. What's the transient of that look like if I kicked the system and let it shake? How is it going to shake? Or what's the mode? What's the structure of the transient response of the closed loop system? Pardon? 1/2 to the n. Now you have to just make sure that you set z plus 1/2 equal to 0. The 1/2 is right, but it's minus, isn't it? So it's minus 1/2. So now our structure is alpha times minus 1/2 to the n, because we found this by looking at that. And you've probably seen all the signs. I buy ugly homes. This might be an ugly transient, right? It's flopping back and forth between plus and minus. You may not like that. It's not. It is collapsing. It's collapsing at a rate of 1/2, but now every time step we change the sign. So this may be ugly. What's the DC gain? Of our closed loop system with, let's say, K is equal to 1/2. How do we find that? We just look at Z equal to 1. That's how we find our DC behavior of our closed loop system. We evaluate this at 1, and we end up with 1/2 over Z, which is now 1, 1 plus 1/2, or we have 1/2, over 3.5, where our DC gain is 1/3. Suppose we put in a unit step to this system. Then R sub SS is 1. So now we're saying we're applying a unit step. And what's Y sub SS? Well, in general, that's now, since our closed loop system was stable, we just take the DC gain times the constant that we applied to the system, which in this case was 1. Or we now have an air steady state of 1 minus 1/3, since our DC gain was 1/3 and we're scaling it by 1, we now have an air of 2/3. We put in 1, we get out 1/3. Is that acceptable? Depends on the system. That wasn't very hard to produce, was it? As a system, we just had to crank up our gain K to 1/2. But maybe this isn't acceptable behavior. The transient maybe wasn't very nice, and the steady state accuracy may not be very nice. So if we wanted to improve our steady state accuracy, let's say I put in a 1 and I wanted to go to 1. I want 0 air. Well, now I may want to pull in my open loop gain, the product of the controller with the plant. I want there to be a pull at Z equal to 1. And to get that, I'm going to have to change the controller structure because I can't change the plant. The plant was just 1 over Z. So now I'm going to change the controller structure to maybe improve steady state behavior. And PI controller gives us better steady state accuracy than just the P controller. PI control enhances the steady state accuracy. Good. So I labeled that 3A. This is now 3B. So now we have 3B, which is the PI control. Or we have 1 over Z, that's the plant, that hasn't changed. But now if I'm putting in a PI controller, what's the controller block look like? There's our PI controller. And we now just connect it up in the conventional manner. Here's our reference input. Here's our output Y. Do you see? All I had to say was PI control, and boom, I can immediately put that structure into my controller transfer function block. I have two adjustable parameters now. I have a K and an alpha. What's my closed loop transfer function? Expression-wise, what's T sub C of Z? That hasn't changed, has it? It's still CG over 1 plus CG. What has changed is what those contain, C and G. But structurally, this is still good. What influences our closed loop dynamics? It's the denominator of that transfer function. So we're now looking at that. And if we plug in our values, we have K, that was part of our controller, and we have the zero factors and the pole factors from our plant and controller, where this is what we can say is our G bar. This is now our N of Z over D of Z, and all of that's supposed to equal 0. And this is Z minus alpha over Z times Z minus 1. What does the magnitude condition give us? Or eventually we're going to try to sketch the root locus, aren't we, of this? But before we do that, maybe somebody wants a formula for K, and they want to just play with K. The magnitude condition says the magnitude of K, G bar of Z is equal to 1. Just solving that equation. Or we now know that K, Z minus alpha over Z, Z minus 1, that's equal to 1. And if we solve that for K, we now have the magnitude of Z over the magnitude times the magnitude of Z minus 1 over the magnitude of Z minus alpha. Well, that didn't help me a bit. Yes, question?
Yes, for the denominators of the CZ, is that always Z minus 1 or the 1?
So now I think the question was the structure of this. If it's a PI controller, what do we know the denominator factor looks like? It's always going to be Z minus 1. That's fixed. Was that your question? So that's always fixed, and the only adjustability we have is with the gain K and this 0 location alpha in the expression for C of Z. Well, what's alpha, for crying out loud? What do we pick it to be? Well, that's why we probably get a little nervous. And we say, I don't know, what do we pick for alpha? Let alpha equal what for this example? What makes you nervous is the fact that choices exist. Alpha could be a lot of different things. We have a choice, but that's why they pay you decent money instead of just somebody off the street. I think I heard a PI control. Well, you know how to design now a PI controller. We're going to try to figure out how to design a PI control. So what do we look at? Well, let's look at the root locus of this. What do we know? Well, we do know some things are fixed. What can we sketch in our z-plane automatically from this information? If somebody says, sketch me the root locus of this system, what do you know you can put down immediately? You can put down two poles, right? One is at the origin and one is at z equal to 1. So let's put those down. We now have a pole at the origin and a pole at 1. Here's where the choices come in. Where do we put alpha? Where do we not put alpha? Maybe I shouldn't even entertain that. But you don't want to cancel unstable poles or zeros with poles and zeros. We only have a 0, so we can use that to put wherever we want. Suppose that I said, you know what, I want to simplify my life. I'm going to put a 0 right there. Is that okay? I've now picked alpha equal to 0. Is that okay? I've just canceled a pole. Can I cancel a pole there? Where can I cancel poles and zeros? Inside the unit circle. Probably don't want to be close to the unit circle in practice, but inside the unit circle is okay for canceling poles and zeros. You can't cancel poles and zeros outside the unit circle. We learned that from Ragazzini. So this is now a stable pole zero cancellation. And the answer is yes, it is okay. What's the root locus look like for this choice? So now on the exam, somebody says, oh, design a PI controller for this system. And the system was 1 over z. And you're going, really? He wants me to design a controller for that? Well, we did. We did a proportional, and we weren't too happy with it. Remember, it was minus 1/2 to the n. Banging around, and we had a steady state accuracy problem. Now we're trying to improve that. So now I said, give me a PI controller. You go, okay, I pick alpha equal to 0. Now what does that tell us? Can you sketch the root locus now for this picture? And what have you actually done by canceling that pole with a 0? People are commenting about VR, 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 virtual reality, right? We can play VR all day. We can put on our VR goggles and we don't even see that pole 0 that canceled, right? Now effectively we just have a 1-pole system with a pole at z equal to 1 and sketch the root locus of that. We already did it when z was at the origin. Now it's not much different. We can stand where? And like our bread. As long as we're between 1 and minus infinity, that belongs to the root locus. Did you have a question or an answer? You had an answer. Root locus is? Was that your answer? Well, I don't even remember my question. Oh, setting alpha to 0, and that's okay, isn't it? Yes, because it gives us a stable pole zero cancellation. What's our root locus? It's that half of that 2 halves of our bread, and now we have a k. Do we have a range of k for stability? Can I just pick any k I want from 0 to infinity and be happy? Well, it depends on who you are. I guess you could be happy even if your system was unstable, but we won't be in this class. Okay? What are some... Can we quickly determine the range of k for stability? Is k equal to 0 okay? Yeah, I mean, we want to be a little bit bigger than 0, but we'll say k bigger than 0. How big can we make k? What are we looking for? We want to know what k pushes that root locus, or the poles on that root locus, outside the unit circle. And the place that goes beyond or outside the unit circle is when we get to minus 1. And what's our expression for k? K was this, so now we had k is z minus 1 over, and we had alpha equal to 0, so those two didn't even need to be there. K is now this. We want to check this gain value when z is equal to minus 1. These are so difficult. I apologize for all these difficult problems, but now we need to find the magnitude of minus 2. That's as big as we can get k, right? So now we have k at the square is equal to 2, and our range of stability, well, let's not even go there. Let's say it needs to be less than 2. So k being bigger than 0 and less than 2 gives us a closed-loop stable system. That was one choice of alpha. How many choices of alpha do we have? Wednesday we're going to have 100 people in here. We have 100 correct answers. I can design some pretty lousy exams to grade, because now there's 100 exams that could have the correct answer, which is fine. It's just a pain to grade. But now, what else? We could now say, well, let's pick a different alpha. Somebody else could say, what if alpha is minus 1? What was alpha? That was the location of the 0. Now what do we have, picture-wise? Well, we haven't changed where we started. We continue to have that. Now we've placed a 0 where? At minus 1, haven't we? So now we have a 0 over here at minus 1, and now we're in the restaurant. We've got bread, we've got a restaurant. Two poles walk into a restaurant with a 0. But the 0 has to be on a particular location relative to those poles, and now it is. Now we have our design, don't we? Our root locus shape. How many branches do we have of our root locus? 2. Which segments, which real line segments belong to the root locus? I've already given you one answer. Now it has to be less than negative 1. What's our pole 0 excess? 1. So how many branches of our root locus diagram are going off to infinity? What was our pole zero excess? 1. We have one branch going off to infinity. That's the big arrow going to the left. Another branch is coming back to that 0, the finite 0. And we have to connect those two pieces. And that's where this 2 poles to the right of a 0 comes in. Now we have a circle. What's the radius of that circle? It's the geometric mean, isn't it? So now we're looking at the distance between the 0 and the pole, first pole, and we're just dealing with lengths, and we have the length from -1 to 1. So we now have the square root of 1 times 2, square root of 2. So where are we? 1.414. Are we right there? Is that our radius? Is that our breakaway? No, that radius is from the circle. Right? So now we go 1.414 from the center, and we should be, let's say right there, 0.414. And where are we to the left of -1 when we re-enter? That's the breakaway point right there. Here's z sub b. That's the breakaway. Where's the re-entry? It's 1.414 to the left of -1, so we're over here. Wow, boy, this is going to be hard for me to draw. There. So now we have this. Do we have any stability? Any chance at stability? Where's our unit circle? Don't hold me to this, but that's the unit circle. And can you now, if you were running out of time like we are now, and I ask you for a range of k for stability, and you picked alpha equal to -1, what would you draw and how would you determine stability? Is there a range of k for stability? We need both branches to simultaneously be inside the unit circle, and that will be giving us closed loop stability. Do we ever have both branches simultaneously inside the unit circle? As long as we crank up k bigger than 0, both branches are real, or both closed loop poles are real, and they're approaching that breakaway point. When we get to that point, and you could find the gain k to get you there, then what? Do you see that once we hit that point, we would be beyond stable? K, and you could say, oh, this is now closed loop stable for K living between K box and 0. But now we could actually sort of quickly think about what we have here. What's this? Distance. And why did I draw that box where I drew it? I've drawn a radius, and that radius is the square root of 2. But that's the hypotenuse of a right triangle that has a side of 1, a horizontal side of 1, an imaginary side of 1. Doesn't that have a hypotenuse of the square root of 2? That's why I can now say that box is actually at J1. It's right on the imaginary axis. I could compute the k to get me there. If you do that, you should find that k is actually going to equal 1. Are there other values of alpha? I said there were 100. I've shown you 2. What are some other options for alpha as we play the credits to this exciting movie that you're watching? Alpha could be between 0 and 1, could it not? Could you sketch that root locus? And could you find ranges of k to give you stability? I'll maybe put in another value for alpha after class, and you can put in one of an infinite number and see if it's going to give you a range of k for stability for that system. But what do we know is happening in the steady state accuracy? If I put in a 3 for a reference, what's y going to go to? It's going to go to 3 because we had a pole at z equal to 1. We forced 0 steady state error due to a constant because of the PI controller. We'll pick up at that point after the exam with PID controllers, etc. But that's enough for now.